is a short video about the lab we will be doing this week. I guarantee you, if you watch it to the end, you will be more efficient and done in the lab quicker. All right. So this is called changing ice to water and steam. And what we can get from that is the heat of fusion, the heat of vaporization. What's not listed is the specific heat of water as well. So we're going to create our own little heating curve and measure the energy it took to melt ice, right? So heat of fusion is melting ice. Specific heat is energy required to heat up water. And then, of course, heat of vaporization, energy required to vaporize water. And so those three values we will then also compare and to the literature values. And the background for that is towards the end of the first chapter, which is chapter 11 on intermolecular forces. So towards the end, I show you these heating curves where we take here in this example, we take ice below its freezing point. We warm up ice. That's the specific heat of the solid. Then we melt it. So here, right here is where we have the specific heat of fusion. Then we have the not specific heat, delta H. Specific heat are only the stretches where you're changing temperature here, right? So we have these three sections where but I don't really want to give you this background because you're supposed to watch the lecture. So let's just look at what we're doing in the lab. Here are the steps. You'll use a 600 milliliter beaker. You're going to pour 200 milliliters of water in there. You're going to measure that exact mass so that we know how much we heated and boiled and whatnot. And so you use that vernier. I'll kind of go through this. We'll use this vernier here. We'll hook up the thermometer, and it's going to measure the temperature of this solution over 3,000 seconds, or as long as it takes to go through the melting, warming, and boiling period. And so you'll tap on this thing. You'll change the sample rate and the time. It also has to be time-based. This is on the instructions, but see this thermometer is connected. And so you start out with just water, but we want this water to be at the freezing temperature, so as cold as possible, because we want to dump ice in there. We're going to dump some ice cubes in there, and we want them to melt at that at the freezing point, which is at 0 degrees. So we'll have to use ice water. You pour 200 milliliters in there, then you dump the ice in, then you press play and it starts recording. Then you crank the hot plate here to full, to have a full output. We know the energy output. I'll show you that when we are in the lab. And so what we're going to create is this graph here. So it's going to increase. It's going to start melting. And in my example here, it took 292 seconds to melt that. So from the time and the heat output of the balance, the hot plate, we can then determine the energy required. And then if we know how much ice we melted, we can get to the delta H of fusion. You're going to continue collecting. You're going to continue heating. So once everything is melted, of course, you'll see the temperature start to pick up, because now we're just warming up water all the way to the boiling point. And so the second segment here, from 292 to 999 seconds, which is 707. So I subtract out the time it took to melt. The second part is heating now, and we can use this time, 707 seconds, to determine the specific heat. And then you're going to continue heating that for a little while. You're going to boil off some, right? So here we now see the temperature stay again like we did for melting. This is melting here, delta H of fusion. This is the specific heat. And then this last segment is the delta H of vaporization. Again, we're going to subtract out the time it took, of course, the 999 seconds all the way to the freezing. We subtract it out, the boiling, and then this is the time it took to boil. Okay, so it has you fill out this table, and this table can be a little confusing. So let me go through this, right? So here we have that 600 milliliter beaker, okay? And you're gonna weigh it empty, and then you can pour in the 200 milliliters, and the difference between the two is the mass of the cold water, the 0-degree water that you have. This here is the cup. You're gonna have a plastic cup. You see it weighs very little, has a very low mass. You pack it full with ice, all right? And by difference again, you get the amount of ice that you added. And after that, this is the same beaker here in the last column. So you notice that the mass of the empty beaker is the same, right? And so this is the mass after boiling. Now the reason that this mass here is higher than the original mass of the beaker and the water is because we've added the ice cubes. And I think this is where most of the confusion comes from. So we have the cold water plus the ice, which we are melting. So this has to be added together. And then if you want to know the amount that you evaporated, you have to subtract this amount here, okay? So for the first part then, so we're looking at this part here. And so I would suggest that you write the time down when you see that all of the ice melted, because it might not be as easy as it looks here, right? You should normally be able to just go in and see where it plateaued here and here, where we started seeing an increase in temperature. However, some of this heat from the hot plate's actually going to be warming up this, so it's possible that it's not going to be such a nice, clean, visible Q here. But anyway, so we used 292 seconds for this first part. Now, your hot plate on the bottom will have possibly the watts, okay? So if the watts are listed, then you just write that down, and we don't need the amps and the volts. If it doesn't have the watts, but it has amps and volts, you can calculate the watts by multiplying amps times volts. And so this turns into watts, turns into joules per second, and we can easily or nicely use that to calculate the heat output from the hot plate. So if this first part took 292 seconds, all you do is you multiply that by the 542.7 joules per second to get Q here, okay? So this will give me 158,000 joules. That's large. And so to get the delta H of fusion, I divide it into the mass, this energy into the mass of the ice. Of course, here I have kilograms, so I have to convert that. So it's 158,000 joules divided by 0.095028 kilograms, which equals about 1.6 billion joules per kilogram, and that would be the heat of fusion. So 1670000 joules per kilogram, not per gram, per kilogram. Anyway, then the second part is from 292 to 999, so we're using 707 seconds. So the time here is 707 seconds. You use the same fudge factor here to get Q. And for specific heat, what we need to do now is specific heat, of course, the units here which are not shown are going to be in joules per gram per degree Celsius. We're going to assume that the change in temperature is 100 degrees. So whatever the energy here is Q that we calculate from our fudge factor, I might as well write it down. I'm going to look down here on my little cheat sheet. So I got 384,000 joules. So it's 384,000 joules divided by the change in temperature, which is 100 degrees, and then I divided by the mass in grams, and so now we have to add these two together because we are heating not just the original water, we're also heating the ice, which is now melted. So we add this together, and that gives me 262.968 grams. So I also multiply by that, 262.968 grams. That gives me the specific heat. See, the units are always helping me. I need to have per joules per gram per degree. And then finally, we're looking at that evaporation part. So now we're evaporating some of this water. So it's the total time it took for this entire experiment was 1,275 seconds. I subtract the time here, and I get 276 seconds. Again, from the 276 seconds, I multiply that by the fudge factor here, which is 542.7 joules per second. And from that, I get the time, the energy that was used to boil some water off. So that's 149,800 joules. And then the delta H, the units here, which I again conveniently do not show, is in joules per kilogram. We're going to do joules per kilogram again. And so in order to figure out how much we evaporated, we need to use the combined mass of this and subtract that out. So what was that again? That was 262. This is unfortunate. 262 point, doesn't matter. This and this together minus 231.9 grams is roughly, okay, this is pissing me off, 31 grams. So we divide that by 0.031 grams, shoot, that's kilograms, to give us the delta H of vaporization. Okay, that's it for the lab. Blah.